So basically the water relation of Populus fremontii here in the Sonoran Desert. So as you can see over here, Populus fremontii are really important species for us here in the Southwest because it's a foundation species of the Southwestern Riparian forest. Southwestern Riparian forest is a hot spot of biodiversity. It's the most important we have here in the Southwest. However, this tree is a groundwater dependent, drought intolerant, even though you find it here. And optimal temperature is between, for photosynthesis, between 28 and 33 degrees Celsius. So another thing that's very interesting is the wide range of geographic area that you can find them, all the way from Northern California to Central Mexico. Also, you can find it in different elevations, 0 to 2,000 meters elevation. And this is the question that we have. What is the difference between these different populations that are from 2,000 meters elevation or 0 meters elevation? So we're expecting to find physiological and morphological traits that are very different and explain local adaptation. So, and these are our goals: identify that kind of traits and explain why, how they work and how they explain local adaptation. So, and that is gonna work, that's gonna simplify our understanding how climate change is gonna affect these trees in the future. So we planted a common garden with 4,000 trees in 2015 in our Free National Monument, Central Arizona. And we are gonna, planted 8 different populations that represent the entire elevational gradient of the species in this garden. We decided this garden, the location, because it's in the mid of this gradient. So it's 0 to 2,000. We got this garden at 988. It's kind of half. So we're not stressing anybody. Everybody's kind of happy over there. And we have, you see the elevations of the different populations. So we represent the entire elevation from 72 to 1940. So we have the entire elevation, but also the mean annual temperature. You see by the side of the dot how they change in size is because the largest dots are higher temperature, the smaller dots are much cooler temperature. Also, you see the red versus blue dots, and that's we're divided into ecoregions, what is called the Colorado or Utah high plateaus, and the Sonoran Desert, where we are right now. So you see the temperatures are kind of really different and the elevation. Another way to see this is if you see the blue and the red lines, so you see how the Utah high plateau population experienced around 3 months of freezing temperatures, while the Sonoran Desert never experienced that kind of temperatures. On the other hand, maximum temperature, you see that the Sonoran Desert experienced very hot temperature between 38 to 41 degrees Celsius. And remember, I said the optimal temperature for photosynthesis is between 28 and 33. So these are way above the optimal temperature for photosynthesis. And this is right now. We're expecting temperatures getting hotter. So this is our hypothesis. Low elevation relying how they survive these already really hot temperatures is by having more acquisitive traits, so they take a lot of water, a lot of resources, very fast, very efficient, and cool down their canopies. The only way to do that. High elevation, on the other hand, they have to deal with freeze. So they're going to be more much slowly, because they want to protect their tissue, leaves, and also their internal xylem from freeze cavitation. So we measure different functional traits, and these are our expectations from these different traits. I'm going to explain them as I go in the results for timing. So the difference in air to leaf temperature, we went with a thermal camera, and we saw for the entire season, a growing season, the temperature of the leaf. And we compare with the temperature of the air. So in 0, this is the temperature of the air in the garden, and these are the leaf temperature averaged by population. As you see, by elevation, as we start going up in elevation, the leaves turn to be hotter than the air temperature. The low elevation tend to be cooler, even 4 degrees or more than 4 degrees cooler. Separated by ecoregions, you see that's very clear distinction between the 2 ecoregions. Characteristic leaf dimension, this is a measurement of 0.7 to leaf width. It's a measurement in physiological about how big the leaves are. And see these 2 pictures. So these are collected from the Utah high plateau populations. These are from the Sonoran Desert, and you see a clear difference. And you see over here in my regression line, you see how they tend to increase in size, and we increase the elevation of these populations. Stomatal density. Stomates, they help to do the transpiration, and we see the same pattern here. Very abundant stomata in the low elevation population. As we start increasing elevation, we see bigger stomata, but much less stomata. So putting these things together, we're thinking that the stomata, the abundant stomata, the smaller leaf explain the difference in leaf temperature. Basically, very small leaf, they get less heat radiation, less convection gain, but at the same time they have more stomata, so they're transpiring more and they're cooling down their leaf much efficiently than the Utah high plateau populations. Another way to see this, I run a principal component analysis, PCA, and trying to identify these two different approaches, or these two different strategies. One to cool down their leaves, the other one to protect their tissue from freeze. So you see here, this is the principal component one, positive and negative from 0. So here we see a positive correlation between leaf temperature and characteristic leaf dimension. I just mentioned that. But it's negative correlated with stomatal density. That's what I just said. Let's see the other traits that we have here. So this is a specific stem density, how dense the stem is. And we found it correlated with the high elevation population traits. And that makes sense. They want to be more dense to protect their xylem from freeze cavitation. So that goes very well. In the other side, we see the sapwood to leaf area. Sapwood is that, let's say, branches. More branches for leaf area. And I dropped these little drawings here. So the green compared to the brown branches. You got more branches, you got more supply of water for your leaf. You got more leaf, you have more demand, but not enough supply. And this is what the low elevation populations want. More supply of water for leaves, cool down their leaves. So, and go correlated with stomatal density, high stomatal density. So at the same time, it doesn't matter that you have more branches if this branch doesn't have enough xylem. So we measure also the xylem area in these branches, and we found that the low elevation population, the Sonoran Desert, have more xylem area than the high elevation population. And they correlate with that kind of trait. The strategy is to provide more water to the leaf to cool down their canopies. I also put every trait by population, and you see here is the elevation, and you see how nicely they group to the left of the PC1. So that is the trait that explain cooling down the leaves. At the same time, the high elevation population group to the right. That is the trait that explain conservative, freeze damage conservative traits. The only population that goes in between is the San Pedro River southeast from here. That's in between because this is 12 meters elevation, so it's kind of in between high elevation, low elevation. But when I'm doing the same exercise with putting by ecoregion, it's clear the definition, and this is a 95% ellipsis, so that they are very distinct strategy for water use. I also run a subflow thermal dissipation probe while I was taking all this measurement from June to October, and here you see every dot is the mean daily transpiration rates. In red is the Sonoran Desert, and blue is the Utah High Plateau, and you see that all the time the Arizona ecoregion got higher transpiration rates here by grouping together the entire season. I was wondering about this last part on August, September, that it tends that the transpiration rate of the Arizona ecoregion tends to be much higher than the Utah. I was wondering why that happened, and I put in my graph also the rainfall in millimeters here, and I see that the monsoon might be the explanation. So we have a monsoon season over here. The water content in the soil might get more replenished, and that might explain that after it's a lag effect, that they can have more water, they transpire more, and that's why the difference here. So a conclusion, I can say that these low elevation populations here in our region are going to need water in order to survive the increased heat and for climate change. The problem is that we're getting much more stress because agriculture is growing here. Cities like Phoenix and Tucson are growing so much, we are depleting these water sources for these trees. So thank you for all the agency and the person that helped me, and that's all. I can take questions. We have time.
So you showed in one of your images with the Arizona leaf phenotype, there's quite a lot of variation in that. I was wondering if you see that plasticity showing up specifically in a seasonal fashion related to monsoon.
Yeah, we are doing this experiment together with Northern Arizona University, and they are running the entire genome of the species, and they have found a lot of plasticity in the Arizona, the Sonoran region. Yeah, and having a problem for me because they have, all the time they have this kind of big error bars. So.
I noticed your stem density correlated with high elevation and freezing.
Yeah.
Did you check the vessel diameter? It's because stem density has multiple drivers, where the mechanism of freezing tolerance is the diameter or the volume of the vessel.
Yeah, I haven't checked that.
Is it easy to measure